Okay, I'm going to go over the bonding notes. So we'll go ahead and start off with ionic bonds. Um, so why do elements form compounds? And there's lots of reasons you could give as why this happens. We'll go with so they can fill energy levels. So something like sodium wants to dump an electron, so it can look like the last noble gas, which is neon. And you could talk about chlorine, which is trying to gain one electron, so it can look like the noble gas argon. And so when those two things come together, they can form a bond simply because one of them is positively charged and one of them is negatively charged. So one way to look at why atoms are gaining and losing electrons is because they want to look like noble gases. And so that gives them a charge. And so since they have a charge, they have an inherent attraction towards the opposite charge. So in an ionic bond, that's what's happening. If I'm looking at the actual electron configurations, the electron configuration for sodium is here, 1s2, 2s2, 2p6, 3s1, and it's this one electron that it doesn't actually want. So if it gets rid of that electron, this portion of the electron configuration, that's neon's configuration, and that's a stable atom, and so that's what it wants to look like. On the other hand, if I'm looking at fluorine, fluorine's 1s2, 2s2, 2p5. What it wants to do is be 2p6, and then it will look just like neon. So both fluorine and sodium are going to try to look like neon because that's the closest stable atom electron configuration to their position. And so I have fluorine losing an electron, I have fluorine gaining an electron and sodium losing an electron. And if I get elemental sodium and elemental fluorine in the same container, they will violently react. So the fluorine can gain that one electron that the sodium is trying to get rid of. We talked about Lewis structures a while back, and they were really just us having a way to look at dots, which represent those valence electrons, those electrons that are going to do some reacting. We talked about the definition from chemistry. We talked about the study of the property of matters and actions of electrons. These are the actions of electrons doing something. So if I could show you which electrons are doing something, it would be easier. So that's what the Lewis structure is. And so here's sodium gets 1 dot in its Lewis structure, and here's chlorine gets 7 dots in its Lewis structure. So the reason the sodium gets 1 dot, the way that you know this is that it's in column number 1. And the way that you know chlorine has 7 electrons for its Lewis structure, 7 dots, is it's in column number 17. And then the way that you would see that in the electron configuration is this 1 dot is this 3s1 electron right here. And this 3p5 wants to be a 3p6. So there's 5, 6, 7. So energy level 3 has 2 electrons in its s and 5 electrons in its p. But what it really wants is 8 electrons in its p, in its third energy level, 2 in the s and 6 in the p. So it can look like argon. And so the sodium willingly gives 1 electron to the chlorine. So now the sodium is a +1 charge, the chlorine's got a -1 charge, and they connect up next to each other because one's positively charged and one's negatively charged. That's it. There isn't anything else to it. The resulting electron configurations look like this. This is neon's electron configuration, and you can see I've got a +1 charge here for the sodium because it lost its 3s1 electron, and a -1 charge here for the chlorine because the chlorine picked up 1 electron, and now it's 3p6 instead of 3p5, and it looks like argon. Okay, so let's talk about covalent bonds. So in the ionic bond, I've got a transfer of electrons, and in the covalent bonds, I have a sharing of electrons. And the sharing is because the atoms themselves are not satisfied with their electron configurations, but they're also not powerful enough to take the electrons away from whatever it is they're making a bond with. So it's really easy to see that with fluorine. Fluorine is exactly the same electronegativity. It's the same atom. And so the fluorine atoms each are missing 1 electron. You can see in their Lewis dot structures, the fluorines both have 7 dots representing the 7 valence electrons. So the black fluorine's got 7 dots, the red fluorine's got 7 dots. And so what they do is they share 1 electron between them. And so now what you see is, if I ignore this part right here, this looks like 8 electrons. And so that fluorine is happy. And this fluorine is happy, 8 electrons. So this is why fluorine is found as F2. It's one of the diatomics. It is not ever found in nature as just a free-floating fluorine atom, because it needs to make some kind of bond. And if it can make a bond with itself, it can create this one single covalent bond. So anytime you see 2 dots drawn between 2 atoms, that's going to be a single bond. In this case, a single covalent bond, because these 2 things are the same, meaning they don't have a much of a difference in electronegativity. So yeah, the electron configuration is this, and then in the covalent bond, it looks like this. So this red electron spends some time around the black fluorine, and this black electron spends some time around the red fluorine, enough where it satisfies their need to have an octet. It doesn't do a very good job of satisfying it, and the reason that I know that is because fluorine is very reactive. If it has the ability to take an electron, it will do it. So since it can't take an electron from another fluorine atom, it's just hanging out next to another fluorine atom until another atom becomes available and it can steal an electron from it. So you can see oxygens do the same thing. They're O2s, and nitrogens do the same thing as well. They're N2s. So these are 3 of the diatomics, 3 of the 7 diatomics from the periodic table. How does oxygen do it? Well, oxygen only has 6 valence electrons on each of these atoms. And so what it does is it puts 2 electrons up per atom. And so I see 4 electrons in between here. And so that results in a bond here and a bond here. And so you get a double bond between the oxygen. So where the diatomic F2 has a single covalent bond, the diatomic O2 has 2 bonds, has a double bond. And now nitrogen only has 5 valence electrons. So what it does is each of the nitrogens offers up 3 electrons to share with the adjoining nitrogen. And you can see 3 pairs of electrons there. So that would constitute 3 bonds. And so that would be a triple bond. There's no such thing as a quadruple bond. I can go as high as a triple bond. So single, double, and triple, and that's it. So mostly the reasoning is because stuff gets in the way. That's a lot of electrons in between the 2 nitrogens, and those electrons don't like each other. So they would be pushing away. And if I tried to put out another set, 2 more electrons, so 4 bonds, then those 2 electrons would push the other electrons out of the way, and it wouldn't work. It would be like trying to shove too many negative charges into the same space, because that's what we're doing. So the negative charges would shove the other negative charges out, and I don't get a bond. But this is enough. And so let's talk about the relative strength. Fluorines are the most reactive of these 3. And so what that's telling me is that the single bond between the fluorines is the least strong. Oxygen is quite reactive, but not as reactive as fluorine. And that's because there are 2 bonds holding the oxygens together. The nitrogen, on the other hand, is really inactive, not reactive at all. Nitrogen doesn't do anything in the atmosphere unless something extreme occurs. So during like the burning of wood in a wood stove, the oxygen's getting torn apart and causing the glucose molecules to get torn apart and producing heat and light. The nitrogens are inside the wood stove with the burning oxygen just hanging out. So the nitrogens are almost equivalent to a noble gas in the fact that they're very, very not reactive. What could react with them? Well, what could react with them would be something like lightning. So if you've got lightning, then as the electricity runs through the atmosphere, since 80% of the atmosphere is nitrogen, a lot of those N2 bonds get broken apart. And now if I've got a nitrogen and it's out there by itself, let's say these 2 guys got separated from each other, this nitrogen will do anything it can to make another bond. It might form back up with the nitrogen it was connected to, but if it can't, it could form a bond with these two oxygens over there, because 20% of the atmosphere is oxygen. And so this gives us NO2, and that can be used as a fertilizer. So areas where there's a lot of lightning, there's also very fertile soil. So where do you get a lot of lightning? The plains. So the Great Plains of the United States is the breadbasket of the world. And why is that? Well, you got a lot of lightning there. And so you end up breaking apart a lot of N2s. And then those N2s form bonds with oxygens, and they make nitrates and nitrites that go into the soil and provide nitrogen to plants. So you nitrogenate the soil in a very natural manner. Other places that have lots of lightning, mountains. And what do you have there for the most part? There are lots of trees. And so why is the soil so fertile on Mount Hood? Because there's lightning there, and you get this NO2 combination that fertilizes the soil. So wherever you have lots of lightning, you're going to have lots of nitrogen oxygen molecules that can fertilize plants. Here's another one. So now we talked about some diatomics, but let's talk about things that aren't diatomics. And in this case, we've got carbon dioxide. So this molecule has 2 oxygens and a carbon, and the carbon has 4 electrons that are valence electrons. The oxygens both have 6. So what ends up happening is the carbons offer 2 electrons to each of the oxygens, and the oxygens offer 2 electrons to each of the carbons. And so you can cover up the oxygen or this carbon and oxygen, and what you see is let me grab a highlighter if I can here. All right, so this oxygen is seeing 8 electrons. Great. So that's why that oxygen is satisfied. But this carbon is also seeing 8 electrons. So that carbon is happy. But this oxygen is also seeing 8 electrons. So that oxygen is happy. So because of the sharing of the carbon and the oxygens, I get covalent bonds that are very stable, and everybody's happy because they're all seeing 8 electrons. And so I've got 2 bonds going from this carbon to that oxygen, and 2 bonds going from this carbon to that oxygen. And that's a very stable molecule. And I know that because it's the end product for a lot of molecules, like the burning of that wood, or you're exhaling right now. CO2 is a molecule that doesn't have very much energy. And I know that because it's the end product of the process that gives me energy, which is cellular respiration. So the energy has been ripped out of the carbon is really what's going on there. So these are all non-metals, and the covalent bonds always have non-metals bonding with other non-metals. You won't have a metal non-metal as a covalent. That's going to be ionic, and there's no such thing as a metal-metal bond. They'll form alloys, but it's not technically a bond. All right. Oh, no, didn't want to do that. All right. All right. How do I get out of that? Okay. No. Draw. There we go. All right. So now what we need to talk about is polar bonds. Okay, so I'm going to first start by saying polar bonds are the reason that water does not mix with oil. So you have seen the effect of a bond being polarized many, many times. So what does the word polar mean? So polar is like the North and South Pole. They are opposites, but usually they're linked in some way, even though they're opposites. So a magnet has a North Pole and a South Pole. You can't have one without the other, but they're opposites of each other. And charges are the same way. You've a positive charge and a negative charge. Those are polar opposites to each other. So within chemistry, we're going to talk about a polarity that happens within a molecule that's not a plus or a minus, a full-fledged plus or minus, because that would be an ionic bond. We're going to talk about a partial plus and a partial minus. So these polar molecules will only happen in covalent bonds. They do not happen in ionic bonds. So polar molecules are only going to be non-metal covalent bonds. And it doesn't happen with all of them. And so we'll talk about how you know which one is or isn't going to be polar. So this little symbol here is the lowercase Greek letter delta, and it means, in chemistry, it means partial. It also means partial in math. So partial positive and partial negative. That's how we dictate if something's going to have a bond's going to be polar in nature. Okay, so again, the bonds have to be covalent. They have to be sharing electrons. And what we're doing is we're unevenly sharing electrons. So the classic example is fluorine or hydrofluoric acid. So this is an H with its 1 electron and an F with its 7 electrons. And so they're sharing these 2 electrons between them. So how do I know if something's going to be polar? You would grab your periodic table and you'd flip it over and you'd look for the green number in the bottom, near the bottom right-hand corner, and it's called electronegativity. We had that discussion in Chem 121. And the electronegativity is the ability of that particular atom to attract electrons, pull electrons. And so fluorine is the highest. Its electronegativity is 4.0 or 3.9, depending on which chart you're looking at. And hydrogen is only 2.1. So that might not seem much, but that's a huge difference in electronegativity. Anything greater than 0.5 difference is going to be considered a bond that could be polarized. So what you would expect is to have a cloud distribution, because this has got a bond of electronegativity of 4, and this is 1, is instead of the electrons being even, you've got this cloud of negativeness on the fluorine side. And so what that means is there's more negativeness over here. It's not a full-fledged minus charge, because the hydrogen does get possession of the fluorine's electrons sometimes, but not often. And so what we do is we say this side over here is partially negative, and that's what this partial negative is showing. And so if this side is partially negative because the electrons spend more time around the fluorine, then this side over here is partially positive. And so this is showing a polar molecule. And you can show charge distribution by taking an arrow. You write a little plus sign here. You draw an arrow pointing to where the electrons went. So to designate the direction of polarity, you just point an arrow towards where the electrons go. And on the back of the arrow, at the beginning of it, not the arrowhead side, you put a little hash there so it looks like a plus charge. So this side is positively charged and that side's negatively charged. And so again, the rule is if the electronegativity is greater than 0.5, then it's going to be a polar bond, unless it's greater than 1.9. If that's the case, then the bond is actually ionic and the electron will be transferred. All right, so why is this important? It's important because if the bond is polar, and we're talking about a polar covalent molecule, that molecule will not mix with any molecule that is also not polar. This is the reason water does not mix with oil. Water itself is polar. Oil is not polar, so they do not mix with each other. So you cannot clean superglue with water. Why? Because superglue is nonpolar and water won't attack something that's nonpolar. So if you want superglue to be removed from your skin or removed from something, you would need a nonpolar solvent like acetone or gasoline. Even olive oil would work. It would take a lot longer, but it would totally work. So if there is no polarness to any of the bonds in the covalent molecule, we would consider that molecule nonpolar. If there is polarness to the bonds inside that molecule, then we would consider that molecule a polar bond. Okay, so alcohol and water mix with each other because alcohol has a polar bond in it and water is a polar molecule. They're both polar, but neither one of them are going to mix well with WD-40. WD-40 is very good at removing grease off of a bicycle chain because the grease is nonpolar and the WD-40 is nonpolar. So you're washing away the WD-40, so using the WD-40 to wash away the grease because they're dissolving into each other. That's it. And it's because they're both nonpolar. So the question that we're trying to answer with this polarness is, will things mix with water? If they mix with water, then I know it's polar. If they don't mix with water, I know it's nonpolar. And if it mixes with water is incredibly important because we're 70 to 80% water. And so if I can mix things with water, I could get them into the body. If I can't mix things with water, then those things will not go into the body. So what we're going to do is we're going to draw a Lewis structure. So this is different than the Lewis dot structures. This is actually creating a molecule with the electrons in position. And so we'll talk about how to do it, and then we'll just do it, and it'll make a lot more sense. So determine the total number of valence electrons on the molecule. And so you really just count up the valence electrons. If it's a ion, then I have to add an electron or subtract an electron, depending on if it's positively or negatively charged. I created a skeletal structure that seems likely. I'll put some atom in the middle that it would make sense. And then I'll connect everybody up with a single bond, and each one of those bonds is 2 electrons. So I have to use up all of the total number of valence electrons that I counted up in step 1. And then I put the other dots around the atoms to make sure that the charge is, all the electrons are used up, and I can create octets with all these atoms. And if I can't, then I start making double and possibly even triple bonds to make sure that everybody is satisfied. All right, so let's do water. So if I'm looking at the water molecule, each hydrogen has 1 valence electrons, and the oxygen has 6 valence electrons. So that's a total of 8 valence electrons. So I have to 8 valence electron. I have to manage all of those electrons. Okay. So the skeletal structure, I'm going to throw oxygen in the middle. One way to understand that it's oxygen and not hydrogen is odd man out. Which one of these is not like the other? That's the one you're probably going to want to put in the middle. The other way is, how would you know which hydrogen to put in the middle? You wouldn't. So neither one of them goes in the middle. And the other way is hydrogens can only make 1 bond. So it can't be in the middle of anything. And oxygens like to make 2 bonds. So this is perfect. So I'll put the oxygen in the middle, and then I'll connect the hydrogens up with a single line. Each one of those lines means 2 electrons in a covalent bond. So those 2 lines mean I've used 4 of my 8 total electrons. The hydrogens are happy because they don't want to see an octet. They want to see a duet. They only want to see 2 electrons. So each of those hydrogens here is happy because there's 2 electrons there, 2 electrons there. The oxygen is not happy. It's only seeing 4 electrons and it wants to see 8. So what do? I put lone pairs of electrons around the oxygen, 2 on top and 2 on the bottom. And then that satisfies my oxygen's need for 8 electrons. And that's it. There's my Lewis structure for water molecules. Let's do another one. So we're going to do formaldehyde or methanone. Methanone. And so this formaldehyde is the common name, and methanone is the actual official name for it. All right, so I've got a C, 2 H's, and an O. Each hydrogen has 1 electron. The oxygens have 6 valence electrons, and the carbon has 4. And so that's 2, 6, 4 gives us 12 total electrons. And so I'm going to put the carbon in the middle. Why? The hydrogens can't be in the middle. They can only make 1 bond. The oxygens like to make 2 bonds. And if there are 3 things, then I can't put the oxygen in the middle. If I put the carbon in the middle, carbons like to make 4 bonds. And so at least it can make enough bonds to connect to the 3 different substances. So what I'm going to do is I'm going to connect everybody up with 1 line. And when I do that, that takes care of 6 of my 12 electrons. Why 6? Well, each one of those bonds, remember, is 2 electrons. So 2, 4, 6. And the hydrogens are happy because they're seeing 2. The carbon's not happy. It's only seeing 6 of 8. And the oxygen's definitely not happy. It's only seeing 2 of 8. All right, so I got some options here. I can take my 6 leftover electrons and put them here. And so now my oxygen is happy. It sees 2, 4, 6, 8 electrons, but my carbon's unhappy, 2, 4, 6 electrons. If I take a couple of those electrons and put them on the carbon's happy, 2, 4, 6, 8 electrons, but the oxygen is not happy, 2, 4, 6 electrons. It's missing 2. So when you get into one of these situations, then you take 2 of those electrons and you turn them into another bond to the thing that is missing electrons. So we make a double bond. So now I've taken these 2 electrons here, I've added them as a second bond. So that bond is 2 electrons, that bond is 2 electrons. There are 2 electrons there, and there are 2 electrons there. And so if I go back to my little highlighter thing, this oxygen sees 8 electrons, and that makes it happy. This carbon is seeing 2, 4, 6, 8 electrons. And so now that carbon is happy. And so doing the double bond allowed me to create a molecule that is satisfied with its number of electrons. And there's the Lewis structure for formaldehyde. And remember, we're doing this so we can determine if the thing can mix with water or not. All right, so let's move on. So now let's talk about some octet rule violations. And octet rule, remember, is that things want to see 8 electrons. All right, so these violations, they're going to be centered around aluminum and boron, and then phosphorus and sulfur. The aluminum boron, they only want to see 6 valence electrons. So don't try to attach a 4th bond to them. Just only 3 bonds to the aluminums and 3 bonds to the borons. So here's aluminum chloride, and it just looks like that. And it looks weird to me, but it's supposed to look weird. The other two, the phosphorus and the the sulfur, the difference in this case is they'll accept more electrons. And the reasoning behind that is because they have they have no electrons in their 3d orbitals, so they can accommodate those extra electrons. So you can see that phosphorus here in the phosphoric acid has 5 lines connecting it. Everybody else has the 8 or 2 that they're looking for, but that phosphorus is seeing 2, 4, 6, 8, 10 electrons, and that's going to be okay. The same situation over here with the sulfur, but even more so. The sulfur's got lots of lines to it. So this is sulfuric acid, and that sulfur is seeing 2, 4, 6, 8, 10, 12 total electrons, but everybody else is happy. So that's the way you work it. If you're building an electron or a Lewis dot structure, you build the Lewis dot structure, and then if you've got extra electrons and you've got a sulfur or a phosphorus, make it work for everybody else, and then just start tacking on extra electrons on the phosphorus and sulfur like we have here. Okay. Okay, formal charge and resonance. So we use formal charge as a way to figure out what the best Lewis structure is. And what I mean by that is sometimes you can make more than one structure that seems reasonable. And so you want to know which one is best. So you do that by doing this thing called formal charge. And what you're looking for is the smallest numbers for all the atoms. If the atoms have high formal charges, then that's probably not a stable structure. And so we're going to want to choose the structure where the electrons or the formal charge is smaller on the substances. So how do we calculate a formal charge? So formal charge is equal to the number of valence electrons minus the number of lone pair electrons minus half the number of bonding electrons. All right, so let's just do the calculation and we'll see what I mean by that. All right, so this would be an acceptable carbon dioxide structure as far as valence goes. And so would this. This oxygen is seeing 8, this carbon is seeing 8, and this oxygen is seeing 8. This oxygen down here is seeing 8, this carbon is seeing 8, and this oxygen is seeing 8. So either one of these is correct as far as valence goes, but the one on the bottom is the correct one. And so let's see why. So with our first atom here, this oxygen here on the left, what I would do is 6 valence electrons. So there's 6 valence electrons there. So that's my number of valence electrons minus 1 for the bonds. So it's got 1 bond on it, and then minus 6 lone electrons. So we end up with a -1 value. Let's do that again. All right, so this 6 represents the number of valence electrons. Carbon is in column number 16, so it gets 6 valence electrons. Okay, so to that, I'm going to subtract off the number of lone pair electrons. And so lone pair electrons is 6. 2, 4, 6. And then I'm going to also subtract off 1/2 the number of bonding electrons. So this is a bond. It's got 2 electrons. I'm going to subtract 1/2 of 1. 1/2 of these 2 electrons. So that'll be 1 electron. So there's 1 bonding electron. That gives me a total of -1. 6 minus 1 minus 6 gives me -1. So the carbon, it's got 4 for its valence electrons. And I'm subtract off 4 bonding electrons. So there's 2, 4, 6, 8 bonding electrons. There's no valence electrons, no lone pair of electrons. So 1/2 of 8 is 4. So 4 minus 4 is 0. All right. So the oxygen here, the one on the right, it has 6 valence electrons. It's got 6 bonding electrons, 2, 4, 6, and I take half of that, half the bonding electrons. So that gives me a 3. And then minus the 2 lone pairs of electrons. That gives me a +1. So I've got -1, 0, and +1. So those are the formal charges. And for this one down here, I've got oxygen has 6 valence electrons, minus it's got 4 bonding electrons. Half of that gives me 2. And it's got 4 lone electrons. That gives me 4. So 6 minus 2 minus 4 gives me 0. The carbon, same situation in the prior, 4 valence electrons, 8 bonding electrons. Half of that is 4. That gives me 4 minus 4 is 0. And then my last one here is 6. My oxygen again has 6 valence electrons, and it's got 4 bonding electrons, and I take half of that, so that I get to 2. And then I've got 4 valence electrons or lone pair electrons, so I cancel those or subtract those off, and I get 6 minus 2 minus 4 gives me 0. So the formal charges up here are bigger than the formal charges down here, which are all 0. And so this is the correct structure. So let's talk about resonance. Resonance is when a molecule makes more than one structure and none of the structures is any better with their formal charges. So all of the structures exist at the same time. What I mean by that is the electrons end up being shared in a way that you wouldn't expect. So here's carbonate. Carbonate is one of the many polyatomic ions that we have memorized. The Lewis structure for carbonate could look like this. It could look like this, or it could look like this. So since none of these is any better than any of the others, what ends up happening is you don't really have a double bond to this oxygen or this oxygen or this oxygen. These 2 electrons that are in this second bond sort of like jump around from oxygen to oxygen. And so what you end up having, we write these dashed lines, and what that's letting you know is it's not a true bond. It's the electron is sometimes, those 2 electrons are sometimes there, but sometimes they're here and sometimes they're here. And so what you end up doing is you take these formal charges of -1 and -1, so the -2 charge, and we distribute it over the 3 oxygens. And so each of them ends up only having 2/3 of a charge, which is less than a 1 charge, a -1 charge. So the other thing about how we know this is true is there is a specific distance that a single bond between a carbon and an oxygen forms, and a specific distance between a carbon and an oxygen with a double bond. And so if this was true, you would see these bonds here, these single bonds from the carbons to the oxygens would be longer than this double bond to the carbon oxygen. And that's not the case. Instead of seeing a short a double bond and 2 longer single bonds, you see this structure where all these bonds between the carbons and the oxygens are not as short as a double bond and not as long as a single bond. So they're like a bond and a half. So the bond length for a double bond is 116. The bond length for a single bond is 143. And what we actually see is bond lengths of 128 for all of the bonds. So we know that the resonance structure exists. And what we mean by that resonance is the electrons that we would expect to be in a stable bond, like this, or this, or this, are jumping around within the molecule. There's always going to be a single bond between the carbons and the oxygens, but those 2 extra electrons, again, are jumping between each of the 3 oxygens and the carbon. It makes the structure more stable, actually. All right, so we're going to talk about something called VSEPR, and we call it VESPR, and what it stands for is valence shell electron pair repulsion. All right, so this applies to molecules that are covalent that have lone pairs of electrons on the central atom. And let me back up 1 second and say, remember, we're talking about all of this so we can determine if something is going to mix with water or not mix with water. All right, so we've got the Lewis structure here for carbon dioxide. And this molecule is in a straight line. the oxygen through the carbon to the other oxygen is a linear molecule. The bond angles are 180. What that means is if I were to take a protractor and then check the bond angle going across, I would have a straight line, which would be 180 degrees, as opposed to, say, putting the oxygen here and having an L shape or L shape. Then those electrons here and those electrons here would be too close. And so the reason that this oxygen is on this side and that oxygen is that side is if I were to move this oxygen up or down, it would start pushing on the oxygens, on the other oxygen's electrons. So they basically kind of like bang, 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 bang until they're perfectly on the other side, and they have pushed the other oxygen to the other side of the molecule as far away from the lone pairs on the opposite oxygen. So this is a linear structure, and this linear structure happens when the central atom has two things connected to it. Well, what if the structure central atom has three things stuck to it? So then we get into this 120-degree angle. So 360 is a circle, and so the bond angles between these chlorines around this aluminum chloride are 120 degrees. Why? Because if I were to take this chlorine and bring it this direction, it would start pushing on this chlorine, and that chlorine would push back. And so this chlorine's pushing that chlorine up, this chlorine's pushing that chlorine up, that chlorine's pushing that chlorine that direction, and this chlorine is pushing the other chlorine that direction. So they're all stable because they've got those valence electrons on the outside pushing everybody away. And so the way they get as far away from each other as possible is having a 120-degree angle. So this would be a trigonal planar shape. It would literally be a flat triangle. So let's talk about water. The water technically has four things around it. Why four things? Because those electrons, those valence shell electrons, these electrons here, push away those electrons and the electrons around this hydrogen. Remember, this section is called valence shell electron pair repulsion. So these electrons in this Lewis structure push those electrons, and those electrons also push those electrons, and those electrons push those electrons. So what I have is a central atom, the oxygen, with four things around it. Two of the things are atoms, and two of the things are lone pairs of electrons. So what we end up here is a tetrahedral shape. Tetrahedral shape is this shape here, or this shape here. These are tetrahedral shapes. And the reason that there's a tetrahedral shape there is because that's as far as everything can get away. So we'll do this with a lab, but if you've got three things around a central atom, they can be in a flat structure. But as soon as you've added that fourth thing, we go into three dimensions, and they get away from each other by pushing stuff down and away. And so we end up with bond angles of 109.5. That's around the tetrahedral shape. So the way I think about this is if I'm the central oxygen atom, above me, I've got two lone pairs of electrons. Down and in front of me, I've got two lone pairs of electrons. Down and behind me on the right, I've got a hydrogen, and down and behind me on the left, I've got a hydrogen. And so everybody's as far away from each other as possible. This structure is deemed bent for the molecule. So if I cover up my lone pairs of electrons, then all I see is the hydrogens and oxygens, and this is a bent structure. And this is why water is polar. That's it. Why is water polar? Because its structure is bent. If this was in a straight line, then there'd be no polarness to the water. But because it's bent, there is a polarness to the water. So why is that the case? And that's the case because this guy has an electronegativity of 2.1, the hydrogen, and my oxygen has an electronegativity of 3.5. So that means the hydrogen's electrons want to spend time with the oxygen, and this hydrogen's electrons want to spend time with the oxygen. So the overall effect is an upward polarness to the water molecule. And so that's why water is polar, because it's bent. And that was the reason that we did the Lewis structures. If we hadn't done the Lewis structures, then we would have come up with water looking like it looked here, which is straight. And that's not the case. So we come up with the Lewis structure and we create the Lewis structure. And then we think about what this pair and this pair of electrons would do to this hydrogen and that hydrogen, and they would all push away from each other. So this straight structure, this linear structure, is not correct. And what we end up with is a bent structure. All right, so let's talk about what happens when we put pairs, when we put things around a central atom. So I've got a central atom, and if that central atom has two things around it, then my structure is linear. If my central atom has three things around it, the way they get as far away from each other as possible is trigonal planar. And so I get bond angles of 120 degrees. If I'm added another object to it, so think about this being flat and I drop another thing on top and it pushes the trigonal planar structure down and I end up with this tetrahedral shape. If I add another thing, so now there are 5 things attached to the central atom, I'd make a trigonal planar in the middle, and I'd put an object on the top and on the bottom, and this is trigonal bipyramidal. So there's sort of a triangle shape or a pyramid shape going up and a pyramid shape going down, and we call it trigonal because pyramids have 4 sides, but these pyramids are showing 3 sides, and it's bipyramidal because there's a pyramid up and a pyramid down. And then lastly, we've got the octahedral, which is 6 things on the central atom. So I have a square box in the middle, and I have something on top, which forms a pyramid on the top, and something on the bottom, which forms a pyramid for the bottom structure. So it's either bipyramidal or octahedral. So there's a 1, 2, 3, 4, 5, 6, 7, 8 sides to the structure. And the bond angle is 90 degrees. So these structures occur when I put different numbers of objects around a central atom. So we can get names like linear or trigonal planar or bent for the molecule name. If I have a lone pair of electrons instead of a third atom attached, then this guy would be bent. So this is a tetrahedral. If the tetrahedral has a lone pair of electrons on it and 3 atoms, then this is going to be trigonal pyramidal. And if I've got 2 atoms and 2 lone pairs of electrons, then I have another bent structure. So there's the structure for water. This ends up being, this one here is the structure for ammonia, and ammonia mixes with water. We know that because Windex is a thing. The other ones I have options for is this trigonal bipyramidal that can be turned into a seesaw or a T shape, or linear if there are lone pairs around the central. And then I've got octahedral and I've got square pyramidal. Square pyramidal and then square planar. What I really care about you guys understanding is that the water molecule is bent, ammonia is going to be this structure, and why these structures here are important. These ones down here aren't common. The trigonal bipyramidal and the octahedral, you're only going to see those with phosphorus and sulfur because they allow extra electrons to be attached. So how do we draw this in a 3D structure? Well, if I'm only talking about 2 things attached to each other, that's really easy. But what if I'm talking about a 3-dimensional structure, which any atom that's got 4 things attached to it is going to be a tetrahedral. And so this structure here, which is 1,2-dibromoethane, it's got 2 bromines and 4 hydrogens with these 2 carbons. That carbon is connected to hydrogen, hydrogen, bromine, carbon. So that's 4 things. So there's a tetrahedral here. This carbon is connected to bromine, carbon, hydrogen, hydrogen. That's 4 things attached to this single carbon. So then that means that there's a tetrahedral there. So what we do is this line, that carbon, that line, they're all on the same plane. Those 4 atoms would lay on a table flat. But this hydrogen here is back. It's going away from you. And this wedge shape, this is coming at you. So coming at you, going away from you. So kind of think about this as a dog leg going away, a dog leg coming, and a tail here. And that's all I got. Dog's upside down over here. So we wouldn't draw methane to look like this. The methane molecule would look like this. So carbon, hydrogen, carbon, these guys are in the same plane, but then I got a hydrogen going away and a hydrogen coming at you. So you can kind of see that with this ball and stick structure. If I could draw like that, then I wouldn't need to draw with the dashes and the wedges, but most chemists aren't artists, so they're not going to come up with this. So we came up with this idea. And so that's how you show a three-dimensional structure on paper, which is obviously 2D. Okay, that's all I have for this entire set of notes. I'll have you guys watch this and then we'll go over things in class. All right, thank you.